Okay, so we shall continue our discussion on classical theory of radiation. So in this video we will talk about pressure due to radiation, mainly for two cases, which is one for normal incidence and for diffuse radiation. Okay, so we let's start the discussion. Okay, so it is well known from theory of electromagnetic radiation, where Maxwell had developed in the late 19th century, that the light waves, light consists of mainly waves. So theory was that at that point of time, and also the light, whenever it's incident on a surface, it exerts pressure on the surface. So Maxwell had given this idea from his theory of electromagnetic, or in fact the electromagnetic theory, that for normal incidence the radiation pressure is equal to energy density. Okay, so normal incidence means, so a light beam or the radiation that we are talking about here hitting the surface on it's perpendicularly incidenting on the surface. So we'll have two cases. Okay, so for diffuse radiation we will see the case where surface is sort of facing the getting or receiving radiation from all different direction, whereas for normal incidence, so we'll have only that we'll consider case where the radiations are falling on the surface perpendicular to, okay, or along the normal of the surface. Okay, so basic idea is to prove that the pressure due to the radiation is equal to energy density. So we have already discussed about this energy density term in the earlier video. So so where we considered, we have taken that to be U. Okay, so basically idea is to the pressure of the radiation must be equal to U. So we must prove this. Okay, so idea is to prove. Okay, so let's start. So initially, just let's take meaning let me draw a picture that depicts the, so let's say we have a beam of radiation. Okay, let's draw like just to show you that, so this is my radiation, let's say. Okay, so this is going like this and hitting on a surface, let's say surface which has to be, for this case for normal incidence, let's say it is hitting this surface. Okay, all right, so I can name this. I will see what I have to name. Okay, so okay, I think I can. Okay, all right, so let's consider a photon of energy h nu. Okay, so h nu, which is moving with a velocity of light, that is c. Okay, so according to theory of relativity, all say this part you all know, right? So energy of the photon, mc square, mass of the, where m is the mass of the photon, c is the velocity of light, is equal to the, so the the mc square equal to h nu, that is the energy of the photon, and so the mass of the photon is given by this. Okay, so the momentum of the photon we can calculate, which is, we know that from our mechanics, right, classical mechanics, that mass into velocity is a momentum. So the momentum of the photon is given by, so I have substituted this mass from here, and the velocity c already we know. So if I substitute, we will get this expression, h nu by c is my momentum of the photon. Okay, so now let's write this h nu as some script e. Okay, where so the energy or the photon associated the momentum associated with a photon is script e by c, where e is the energy of the photon. All right, so now what will happen, that whenever this, okay, so let me, so I have named it here pq, so let me name this surface as pq. Okay, so it is pq. So your incident, so these rays of lights are falling on a surface perpendicularly, okay, which is surface I have named is pq. Okay, so so now the momentum incident on the surface pq per unit area per second. So please kindly note about the where it is per unit area per second, or meaning these terms. Okay, you have to be, otherwise you will miss the trick here. So the momentum incident on the surface PQ per unit area per second is given by, so see, it's like I'm calculating, let's say one photon is hitting the surface, okay, which is transferring momentum to the surface, let's say, and I will assume that here whatever photons falling on the surface is being absorbed, okay, for our case that we are studying here. So the momentum of each photon, as I have calculated, this is E by C. So E is h nu. Okay. So I am considering now, let's say there are few certain amount of photons which are falling on this surface per area per second. So if I sum up those, so this sum goes from let's say, I mean, those photons which are falling on the surface, okay, per unit area. Like so we have considered in the PQ area, I have considered a unit area, and I am calculating the number of photons which are falling per second. Okay, so the momentum transfer to the surface will be given by simply sum of all those photons which I am considering, the unit area that I have considered, to which number of like photons are falling per second. Okay, so that is given by this sum over this linear sum over E by C. Okay, so sum, anyway, C is constant, so sum goes from the E. So this sum E, or the sum script E, the total energy incident on the surface per unit area per second. Okay, so on this surface which I have considered, okay, so meaning the PQ that I have considered, okay, the PQ surface. So let's say I have considered some area here which is unit area, okay, so on this surface, let's say, okay, so I'm counting, assuming the number of so I'm counting the photons which are falling on this area which is unit area per second. Okay, so so this if I count all those, the energy of each photon is E, script E. So if I sum of all the photons which are falling on this unit area per second, that will give you the total energy incident on the surface per unit area per second. Let's say that energy is E. Okay, so if I just substitute this E in this formula, which I have written here, so capital P, which is the total momentum which is incidenting on the surface, okay, so the capital E by C. Okay, now this part you have to understand. Okay, so the momentum transfer to the surface is this, given by this capital E by C. Okay, so now if small u is the energy density, so this we have discussed in our previous video, this is energy density, meaning energy per unit of volume, then the total energy passing through the area S. Okay, so again I go back to, let's say that area which you have. Okay, so this is my PQ, this is my PQ. Okay, that surface where this light is incidenting, okay, or falling. Okay, so I have, let's say, the area. So I have now considered a area on this. So this is my, so see, for like it is radiations are falling like this. Okay, so I have considered now here on this surface, let's say I have a surface now, this is PQ, who this area, meaning this area, so this surface, let's say, which I have considered has got area S, small s. Okay, let me write like this, small s, this S. Okay, okay, so passing through, total energy passing through the area S of the surface normal to the incident radiation per second is UCS. Okay, so what is the velocity of the radiation, meaning the photons here? C. So how much distance it will cover in 1 second? C distance, right? Because C is the meter per second, that is the velocity. Okay, so in one, so the photon covers, so photon moves or covers distance C in 1 second. Okay, so if this surface has got area S, so I have energy density, so I need to calculate total energy passing through this area. okay, total energy passing through this area, okay, per second. So area, so see, I know the energy density. Density is what? Is the energy density is energy per unit volume. So energy multiplied by volume will give me the total energy in, okay. So the energy density is U. So if I multiply by volume, I will get the total energy. So how will I get the volume now? So area I know. So area into height. Let's say that is my volume. So area is S, so I have to multiply by S. So I want to calculate total energy passing through the area, this area S that I have considered on this surface PQ, which is in 1 second, per second. So in 1 second, distance covered by the photon is C. So that is like a height in this case. So the base is this, my area of the base, you can think about in 1 second, and this is my, let's say, distance covered by C in direction of the propagation of the radiation, isn't it? Okay, so base area into height, that is C. So this much will be the energy, total energy which is passing through the surface having area S in 1 second with velocity C, right? Okay, I hope you got the point. So U is the energy density. So if I multiply by the volume, I will get the total energy. Okay, so how will I get the volume now? So to calculate the volume, I need the surface area, which is like, through which the radiation is passing through, and I need, so this area I know, and I need in 1 second how much distance the photon will cover. That is C. Base area is S. Because I am now calculating total energy passing through this surface in 1 second. Okay, so that is given by this UCS. U is the total, so the energy density, C is the velocity of the photon, okay, or light, and S is the surface area of this through which we are considering that light beams are passing through. Okay, so the energy flux, okay, that is the energy radiation per unit area per second. So energy per unit second we have calculated, UCS. So energy per unit area per second will be, so whatever energy, total energy we have calculated, divided by total area of the surface through which it is going through, that I will get energy flux, which is to UCS by S. Okay, so I will ended up with giving the energy, so which is UC, isn't it? So this capital E is the total energy incident on the surface per unit area per second, or energy which is passing through this surface area, or the energy passing through the plane. I can consider the PQ plane, okay, per unit area per second is given by this UC. So now let's substitute this E, value of E in this expression. What I will get? UC by C, so then CC gets cancelled out. I will remain with U. Okay, so the momentum which is hitting on the plane which is perpendicular to the radiation, okay, direction of the radiation, so that is equal to U, right? U, so the P is equal to U. Now assuming that if all of this momentum is absorbed, okay, it will give, okay, so if all this momentum which is hitting the surface per unit area per second, if it is absorbed on the surface, change in momentum will be what? P, right? Initially it was P, finally it will be, so change in momentum will be P, because finally it will be 0. So it will give and that is happening in 1 second. Okay, so that's why it will give, this P will give you the rate of change of momentum per unit area, because it is already we have considered the P which is hitting on the, meaning like radiation is hitting on the surface, which is per unit area, right? Okay, so that is what pressure. So like rate of change of momentum is your force, but then per unit area it is happening. So force per unit area is what? Pressure. Okay, so that's why there is pressure of the radiation, isn't it? So that's why we got now here P is equal to U. Okay, so what we have considered here is that the idea here is that the assumption we have made that the photons which are hitting the surface, okay, per unit area per second, it is being absorbed. Okay, none of the photon has got scattered or reflected or things like that. Okay, so assuming that all photons are being absorbed on the surface, so there is a change of momentum. Okay, so whatever momentum had incident on the surface, everything is being absorbed. So the change is and that is happening in 1 second. So change of momentum per second is p, okay, which gives you the force, and then that is also we have considered per unit area. So force per unit area is your pressure. Okay, so this is, so that's why we have proved here now that the pressure due to radiation for normal incidence is equal to the P, which is the pressure, and this is which is equal to the energy density of the photon there, or the energy density of the radiation that we have considered here. Okay, so now let's move on to the second part, that the pressure of diffuse radiation. So diffuse radiation means what? Again, we will consider these photons hitting on a surface, but unlike in the previous case where we consider only on the normal direction, we will see that photons are incidenting on a surface from various directions or all possible directions. Okay, so it will involve little bit of mathematics. Okay, so pay attention to that. Okay, so again we will go back to this diagram where, so our main surface is this LM. Okay, so the main surface is this LM, which is on where these radiations, blue color rays that you have seen here, these radiations are incidenting on this surface LM at an angle theta. Okay, so this is your angle theta, which is with the normal to the surface. So you can consider this MN to be normal to the surface. So these rays of light, or the radiation that you see here, or this beam of radiation that you see here, makes an angle theta with the normal to the surface. Okay, now if we apply basic mathematics, that is similarity of triangle, you will see that, so this okay, so this plane KL, okay, this plane KL, so this is your K, this is L, okay, this is your K and this is your L, which is perpendicular to the radiation direction. Okay, or this beam of light. Okay, so or beam of radiation. Okay, so KL is a plane perpendicular to the beam of radiation. Okay, so that means what? So that means that this angle is 90 degree. Similarly, I can draw a rough triangle, so meaning, okay, so this will be 90 degree. Okay, so I'm just trying to match why this angle KLM, this angle is theta. So, and if you apply all these laws of parallel lines, so this line and this LM is parallel, right? Both of them are parallel, so this angle will be equal to this angle. So by applying similarity of the triangle, this theta, angle theta here, this angle will be same as this. Okay, so please go back if you are not familiar with this, but what you have to consider here is that the angle, so the angle, this KLM is theta here. Okay, all right, so let's continue. Okay, so yes, so the energy, again the energy density of this radiation is, let's say, U. Okay, and these photons are moving at the same speed. Again, this is the speed of light, velocity of light, which is c here. Okay, so the energy incident on the surface KL per unit area per second is UC, which we have already discussed in there. So the KL is the surface, which is, or the plane which is perpendicular to the beam of this radiation, and U is the energy density. So UC will be the energy incident on the surface of this KL, which is perpendicular to the beam of radiation. Okay, so this is the energy incident on the surface KL per unit area. Okay, per unit area and per second. Okay, which you have done just few seconds back. Okay, so we have calculated this. Yes. Okay, all right, so yes, so then this energy incident on the surface having the area, let's say S, will be how much? Simply it will be in, okay, so if the surface area is S, if S is the surface area of the plane KL, then energy incident on the surface KL in 1 second will be, so in the per unit area was UC, then for surface area S, it will be UCS, right? But from this figure, okay, let's, so the, what you have considered now, the this area, surface area of this KL plane, or the surface that we have considered, area is small s, whereas the area of this LM surface, let's say, of the plane is S dash. Okay, so if I, what I can do, if I can, you know, think about these two surface, and there is a normal to it. Okay, so this normal of the two surfaces make angle theta, right? So I can write from this that the S is equal to S dash cos theta, isn't it? Okay, we all have done n number of things, I think, in early in different courses of the physics. Okay, so that's why the surface area of KL is equal to surface area of LM into cos theta, right? Because the angle is this theta, so S dash component along the LK or the KL surface will be how much? Cos theta, right? Okay, so that's why we have the surface area, which we consider S, will be equal to S dash cos theta. So energy incident on the surface KL per second, the UCS, so we have already taken here, but in terms of area, because see, ultimately what is happening, the radiation is hitting surface LM, so the KL surface is that we have considered, right, which is, we have taken a surface perpendicular to the beam of radiation, because we can use the results from earlier study, like the previous case. Okay, okay, so the energy incident on the surface KL per second in terms of this LM surface is UC S dash cos theta. Nothing, just I have substituted for S here, right? I have substituted for that. So now the note we have to make that total energy crossing the plane LM per second is equal to the energy incident on the plane LM per second. Okay, idea is what? Now if you consider this LM, so whatever energy is crossing through this, meaning the surface, the beam of radiation which is passing through this, that means that much of energy is being incident on that same surface, right? So that's what has been, and that is happening per second. So here we are considering everything per second. Okay, so so the energy incident on the plane LM per second is what? Yes, same thing, UC S dash cos theta. That's what we have written in the previous slide. So now energy incident on per unit area of the plane LM per second. So here it is what? Energy incident of plane LM, which has got area S dash. Okay, so now per unit area will be how much? The energy incident on per unit area of the plane LM per second. So the LM is this. Okay, so energy which is passing through there is UC S dash cos theta. Okay, so that much of energy is passing through, which is happening per second. Okay, so this much of energy is being passing through this surface LM. So UC S dash cos theta is the amount of energy which is passing through this area LM. So per second. Okay, so per unit area will be how much? Simply this much energy divided by S dash line, that will happen per unit area. So that's what is happening. Okay, so we will need, you know, the energy incident per unit area of the plane LM per second will be the energy which is passing through the surface, and surface area of the plane LM, which is S dash. So ultimately what will happen is S dash will get cancelled, or UC cos theta. Okay, so, and we have already got the formula for momentum, right? Incident on the surface LM per unit area per second, which was energy by, like energy by the velocity of light, which we have seen. So here energy is UC cos theta, which is passing through the surface per unit area per second. So I can write this is like a momentum. So momentum will be how much? So energy is uc cos theta divided by the velocity. So I'll remain with this u cos theta. So this c and c will get cancelled. So this much of momentum is being incident on the surface lm per unit area per second. Okay, all right. Then what I have to consider now? Okay, so I need to consider, like this is only for one photon. All photons I have to consider from different direction. So the component of this momentum in a direction normal to the surface lm. Yes, so I had this surface lm. Okay, so the rays of lights are falling like this. Okay, which is, if you consider the momentum of a single photon, if you can, which is being transferred here is to the surface, is just given by u cos theta, right? So the energy density and then u cos theta. Now this momentum along the surface normal is what? Along this, which was making angle theta here, right? Which was making angle theta with the normal. So along this direction, p is equal to u cos theta. So along the normal will be again this u cos theta and cos theta, because angle is, right, this is normal, our component that we resolve for a force, right? Okay, or any vector quantity for that matter. So u cos theta, which is p, then it will be cos theta. So along this direction, this is p. So along this direction will be how much? It will be p cos theta, isn't it? So, and eventually we will get it. So the component, so the momentum along the direction normal to the surface lm, it will be u cos square theta. Okay. Now assuming that all of this momentum is being absorbed, so then this is the expression for the total rate of change of momentum per unit area normal to the surface lm, isn't it? So this is, so the momentum of the photon which is falling on this surface, okay, this ultimately is giving you u cos square theta. Okay, if assuming that this entire momentum is being absorbed, so that like the previous case, so this is happening per second per unit area. So if everything is absorbed, so there is a rate of change of, so that will give you the change of momentum per unit area and per second. So whenever happening per second, it will give you force, right? Rate of change of momentum is force. Per unit area, it will give you force per unit area is pressure. So that's why the pressure of the radiation on the surface Lm is given by u cos theta, u cos square theta. But now the important point is that you need to account for all the radiation falling on the surface. So you have the surface, so you have considered like this. For now, just because the theta has come into the play now, so you can play with the theta to consider all the wavelength falling on this surface. Let's say so we have considered like for initially to like this, let's say rays are falling like this, like that, from all different possible direction rays are falling. Then how do you account for that? Basically what you need to do now, that you have to integrate over the theta, all the theta. Now theta is what is the angle? Okay, so what you will do now, okay, so in case of diffuse radiation, the radiation is incident from all possible directions that we have already talked about with equal probability. Okay, so therefore, so now we will consider that if you have n beam of radiation meeting the surface, total radiation pressure on the surface is given by this. So like each of these beam, let's say one photon which is exerting pressure on the surface through this momentum transfer that we have already discussed. So u cos square theta. So if you sum up over all the momentum due to all the photons that is being incident on the surface, you will get the total radiation pressure on the surface. Okay, now how do you calculate this term? Okay, so let's start. So you have to consider a hemisphere. Let's say so your surface Lm is here. Okay, surface Lm, the same surface, let's say with being O as my center. So I draw a hemisphere, okay, with this M, A, C, D, as you can see, okay. So it's a hemisphere, it's a, it's a 3D structure, as you can think. The base is circular and then you have a hemisphere on that, okay, and having radius R, let's say. So having radius, so if OL is R, OB will be also R, and this OD also will be the R, okay. So we draw out a ring shaped element AB, as you can see here, this is AB, okay, this is a ring shape, a dash in the other side, okay, and then CD. So we cut out on this surface, you can think about, so I have cut out a ring shape element on that, okay, and with the, by means of a two cones, okay, this semi angle of the cone, so the, if you think this is your theta, okay, this semi angle, so the cone made by OD and C, this, okay, the cone angle is theta, whereas I have taken this another cone which is OB as my, that radius of the sphere, okay. So OB is my another axis through which I have cut out this ring shape element, okay. So where the angle is theta plus d theta, so the total angle for this cone is theta plus d theta, okay. So now quickly what I can do, I can draw so basically I need to find out the area of this ring, okay, this ring ABCD, I have to find out area of this ring. So since this is OD is my radius R and this is my angle theta, so this will be what? R, so this will be given by R sine theta, okay, and the perimeter of this circle CD, which is covered like this perimeter will be how much? So the perimeter of this circle, okay, which is inscribed in circle on a surface of this hemisphere, will be 2 pi r, typically the 2 pi radius, right? So radius of this circle is what? R sine theta. So R. So why am I doing this? Because I will be using these things, okay. And so basically I am just trying to calculate the surface, this area of this ring, okay. How will I calculate? So if I have this perimeter, so I can sort of cut it out and put a strip on this. What I have to do, if I take a perimeter of that, multiply by the, so they like length into breadth kind of thing, right? So one way the length and the other one is breadth. So if I have calculated the perimeter of this circle, and then if I calculate this part which will be given, so since this angle is d theta, so this is like arc length, so arc length will be how much? Arc length will be equal to, so R, so this is OB is my R, so d theta, so this will be given by R d theta, okay. So I can calculate area of this ring by simply perimeter, like 2 pi R sine theta multiplied by this R d theta, okay, so which we will be using in the next slide, okay. So yes, so the area of the ring, that, so 2 pi R sine theta, which I have told you is the perimeter of that CD, the upper ring that we have considered here, perimeter of this circle, okay. And the arc, I will multiply it by arc length, which is R d theta, then I will get the area of this ring element or the ring shape element, so which will be given by 2 pi R square sine theta d theta, okay. Now consider like n, so on this hemisphere, let's say n beams are like continuously the uniformly distributed over the surface of the hemisphere, okay. So like number of meaning what is trying to say that the number of beams are uniformly distributed all over the hemisphere, and this area of the hemisphere, we know that this is 2 pi, so the surface of the sphere is 4 pi square, so half of that will be 2 pi square. So the number of beam crossing through the area of the ring, so we have this strip or the ring, okay. So since it is uniformly distributed all the beams, so how much of that total number of beams are actually going through this ring, so that is, let's say that is delta n or dm. So that will be given by what? The area of the ring divided by total area of the hemisphere multiplied by the total number of beams, right? So this on the numerator it is given by 2 pi r. It is the area of the ring through which the there is these beams of radiations are passing through, and then to the area of the hemisphere. Okay, so ultimately we will get it what? The 2 pi r square will get cancel out, isn't it? So this 2 pi r square, 2 pi r, so I will have this n into sine theta d theta. So the fraction of beams so incident between this angle theta and d theta will be given by simply dn by n, which is sine theta d theta. Okay, so now the pressure P we can write as, so this was what the pressure which was exerting on the surface due to a single photon, right? Now what we have considered, okay, this is okay u cos square theta. So now I have fraction of the beams which are going through this ring shaped area, so I can write that the pressure exerted, okay, by the photons which are going through or passing through this ring is given by this particular expression, because dn by n, which is sine theta d theta, and then multiply the u cos square theta. So simply it will be u cos square theta sine theta d theta. Now we have to consider generalize this thing. So we have to consider all the beams. Okay, so the all possible rings within this hemisphere will be, so the theta, as you can see here from this figure, theta can go from 0 to all the way till maximum pi by 2. So if I integrate over all the theta, then I will consider, or I will cover up all the beams that is falling on the surface from all possible direction. So when I put this and integrate over this expression from 0 to pi by 2, then this is simple integration. So I hope you all are familiar with these things now. I have in fact carried out the entire integration. You have to substitute for cos theta equal to x and carry out. You will get it, this pressure of the diffuse radiation that is 1/3 of the total energy density. Okay, so here see, this is a little bit mathematically involved, basically to cover up the radiations which are falling on the surface from all different directions. Okay, otherwise I think it is pretty simple. So we have learned today the two cases of this pressure due to radiation. One is for normal incidence, where we have seen that the pressure exerted by this radiation when they fall on the surface with normal incidence, then the pressure is equal to energy density. And if it is for the diffuse radiation, where we consider photons or the beam of radiation falling on the surface from various directions falling on the surface, then we have seen that the pressure exerted by the radiation, for that case it will be 1/3 of the total energy density. Okay, so we shall stop here.